Hello and welcome to this SimScale simulation webinar. We will discuss today how to use SimScale to optimize the design of cooling plates used in electric vehicles. Let's start with introducing the use case for today. A design engineer working for an automotive supplier is tasked with improving the design of the battery module cooling plate shown here on the left. The OEM has informed the supplier that they want to use smaller low power pumps to drive fluid through the cooling plate. The design engineer manager believes that the original design on the left will not perform well with this new pump and has therefore tasked one of his team members to come up with a new design with a more efficient cooling performance. The heat that the cooling plate must remove is 400 watt per square meter, while the maximum pressure difference between inlet and outlet is around 2000 Pascal. The temperature on the cooling plate must not exceed 50 degrees Celsius during steady state operation. So this would be a cooling plate that's being used for a battery submodule in an electric vehicle. And the new cooling plate the designer came up with is shown here on the right. And the design engineer will use SimScale to firstly check the performance of the original design and verify his manager's claim. And secondly, the engineer will see how the new concept compares with the old one and if the new one fulfills the new requirements of the OEM. Okay, to start the simulation, let's go to simscale.com. SimScale is completely cloud native, so it runs only in your browser. And all steps, including pre-processing, calculation, and post-processing, happen within your browser. As such, you do not need any powerful hardware to use SimScale. You just need an internet connection and a basic laptop, and all the simulations run on cloud servers. After logging in, I can access my dashboard where I organize my projects, and I'll open the simulation of the original design to analyze the results. So first, let's have a look at the temperature distribution. Right, and we can see clearly here that the 50-degree threshold is grossly exceeded. The maximum temperature reached by the cooling plate is actually around 125 degrees Celsius. So unfortunately, the manager's hunch was very much justified. The original design is very efficient and does not fulfill the requirements. It may have performed satisfactorily with previous pumps that were maybe more powerful, especially considering that it has such a large heat transfer surface area. Right? But since the OEM wants to use a low power pump, we have to redesign the cooling plate. Okay, so let's set up a new simulation on the new design. The first step is to upload the CAD file. We can use any CAD file format or any CAD native format. It does not necessarily have to be a step file. Right, and here you can see some of the details of the new design. And the next step is to prepare the CAD for simulation, meaning specifically that we actually have to create a flow volume. And that's something that can be done in SimScale with actually just a few clicks like you see here. And here you can see what the flow volume looks like. Yeah. And so the next step is to set up the actual simulation after the CAD has been prepared. We can duplicate the existing simulation and replace the old geometry. Yeah. In such a case, SimScale automatically reassigns the materials and boundary conditions, and you can directly run the simulation. However, we want to see how easy it is to set up a simulation in SimScale. So let's first select the module or solver to use. And for this simulation, we will use the Conjugate Heat Transfer module. Yeah. So a simulation tree appears where we can work through the list from top to bottom and make sure all the red rings have turned green and then run the simulation. And this is a very good guide on how to set up the simulation. Right, and so the first step here is now to select the fluid. In our case, it's a 50% ethylene glycol water mixture. Right, and in the next step, we'll select the solid materials, and to make things, or to keep things simple, we'll just select aluminium for all solid parts. Moving on to the boundary conditions. So at the inlet, we'll have a pressure of 2000 Pascal gauge pressure, and an inlet temperature of approximately 20 degrees. Right, and the outlet will have 0 Pascal gauge pressure, so atmospheric pressure. And lastly, we need to define the heat source, which in this case is a heat flux of 400 watt per square meters, and that will be assigned to the flat plate of the geometry here. Right, so the setup is done, and now we can start the simulation. And since we're running this in the cloud, I can continue working, right? My computer is not busy or used for calculations. So for example, I can continue post-processing. I can look at previous simulations and look at the results, analyze the results, or I can run additional simulations in parallel, which is what I'm doing here. There is no limit to how many parallel simulations you can run in SimScale. Previous example, I increased the heat flux to 600 watt per square meter. Or I can also, what I'm doing now is run a parametric study where I'm trying out different inlet pressures, 4,000, 6,000, and 8,000 Pascal. Right? And when I start a simulation now, it will run these 3 cases in parallel. For every simulation run, we set up a new virtual machine with up to 192 cores each. So now I see I'm running 5 simulations. This is as if I have 5 powerful workstations underneath my desk. And there's no limit to how many parallel simulations you run in SimScale. All right, I went ahead and prepared the results to compare the new design with the old design. Let me put them here side by side in SimScale's post processor, and let's look firstly at the temperature distributions of these 2 designs. If we put the upper limit of the temperature color scale to 50 degrees Celsius, we can see that in any region that is completely red, that it's hotter than 50 degrees. And we can see that large portions of the original design here on the left are very clearly above that temperature threshold. On the other hand, the maximum temperature of the new design is under 40 degrees. So it's obviously much more efficient with these operating conditions. This may be counterintuitive since the surface area of the channels is much higher in the old design. Normally the higher the surface area that you have for heat transfer, the better or the more efficient your cooling performance is. Okay, but to understand why this case here on the left with such a high heat transfer area is performing so poorly, we can compare velocities. And that's what we'll set up here. So for a given pressure drop, the flow velocity and volumetric flow rate are much lower in the original design. This means we can see this here on the left. It's light blue, which is about 0.1 to 0.2 meters per second. And on the right, we can see we have much higher velocities, right? And so the lower velocity means that there's a much smaller amount of coolant available to carry away the heat. Right? The manifold channel system of the new design on the right allows for a higher coolant flow rate, and therefore more than compensates for the smaller heat transfer surface area of the channels. So SimScale, or the SimScale platform, has proven to be an invaluable tool for these types of critical redesign processes. Yeah. And this is thanks to several advantages that facilitate an efficient and rapid iterative design workflow. The first advantage is SimScale's user-friendliness. The platform's cloud-native nature allows the entire process, starting from CAD preparation, simulation setup, calculation, post-processing, to run entirely in a web browser without the need for powerful local hardware. Furthermore, SimScale streamlines the iterative process by automatically reassigning materials and boundary conditions when duplicating existing simulations for new geometry. A second large advantage is SimScale's parallel simulation capabilities. SimScale has virtually limitless parallel computing power, and this allows the user to run multiple design iterations or parametric studies, for example, inlet pressure, inlet temperature, etc. And this can be run simultaneously. So for every simulation, you have a new virtual machine. So the entire project structure in engineering design, from checking the poor performance of the original design to successfully validating new, more efficient designs, becomes a very fast and effective iterative workflow with SimScale. And thus, in this sort of more fast-paced engineering environment, especially in the automotive industry, SimScale gives the engineer a competitive advantage compared to more traditional simulation tools. Thank you very much for your attention, and I'll hope to see you next time.